This idea of the LADS, the Laser Airborne Depth Sounder, uses an aircraft flying over water to record the depth of water by sending laser beams and reflecting them off the water surface in the bottom of the sea or ocean. You might remember that we discussed there's two different types of laser in operation here, and one is this color. Actually, there might be a little bit of conflicting information here, and that is that they kind of show that there is only, here they're showing there's one laser, and so, but here's how I want you to see it. I want you to see it as there's a red laser that is shone down from the aircraft. It's reflected off of the water back to the aircraft, firstly. Secondly, there is a green laser that is sent from the aircraft also, and that one penetrates the water. Goes, oh no, I've changed the recolor of that one, haven't I? That one penetrates the water, goes right to the bottom, and then reflects back up. Now, the reason why we have a red laser and a green laser will become apparent shortly. One is, the basic idea is that the red laser hasn't got as much power, penetration power, as the green laser does. And so this red laser here just reflects off generally reflects off the surface of the water. Some might penetrate, certainly. The green laser tends to, some will be reflected off the water in all cases, but tends to go straight through the water and hit the ocean floor, okay? The principle of operation here is simply that the aircraft flies over, shines these laser beams down, measures the time difference between them. So this one has to go down and reflect back up. It only has to travel this distance here, okay, this height, this altitude of the aircraft above sea level. This laser here has to go below sea level, so travel that distance through the depth of water, back up through the depth of water, and then back to the aircraft. Now, that distance there is reasonably easy to calculate, you might see. All you have to do is essentially know how fast this laser is in this medium, firstly, okay, because it's going to be a different speed. Light travels at different speeds through different mediums, so a different speed through the air to what it is through the water. But if we look at the time difference, so how long this laser takes to get down and back up, and the difference between that and how long this one takes to go down and get back up, we have the time it takes to travel this distance here, d. If we know that time, and we know the speed, the approximate speed of that laser in the water, then of course we can calculate the depth of water. So velocity is equal to distance over time, isn't it? Easy enough. In order to calculate distance, from that we get, of course, distance is equal to velocity times time. And here, knowing the speed of the laser in the seawater, and the time it takes to traverse the seawater, d, or the depth, can be calculated. Okay. So let's do an example here. What is the depth? I've got a question ready to go, I think. Yes, this one here. I'll put that back up in a second. I hope you can read that. I'll read it out to you. An aircraft carrying a LADS system is flying horizontally above a lake. Yeah, that there is microseconds. So the laser beam, the laser pulses reflected off the surface of the water and off the bottom of the lake, return to the aircraft 3.33 microseconds and 3.55 microseconds after being emitted. If the speed of light in fresh water is 2.25 by 10 to the 8 meters per second, calculate the depth of the water where the sounding was taken. Okay. Students tend not to have difficulty with these questions, and you might have seen this question in the homework, I'm not sure, or a question very similar to it. So the time difference. Okay, we're going to take the larger time by 10 to the minus, micro is minus 6, of course, minus 333 by 10 to the minus 6 seconds. Equals 0.22 times 10 to the minus 6 seconds. It's not a very long time, the difference between them, of course. Light travels very fast, even in water. The depth is equal to the velocity multiplied by the time. And the velocity is 2.25, they tell us, by 10 to the 8 meters per second, multiplied by 0.22 times 10 to the minus 6 seconds, equals 49.5, thank you, 49.5 meters. I haven't finished though. What haven't I done? Yes, why do I halve it? Yeah, it's got to remember that that's the time it takes for the light to traverse this distance up, down and back to the surface of the water. So we need to halve that to get that depth. But that's from that's from the surface to the bottom and back to the surface. Uh, 49.5 divided by 2 is equal to 24.75 meters. Did anybody notice a question like that in the homework? Yes, there is. Very similar. Basically, they give you 2 times and the speed of the light in the water, whatever water it is, and you do that calculation. I haven't seen much variation other than explaining how LADS works, of course, it has been an extended response in the recent past. Okay, why use powerful lasers? We're almost there. Exactly the same, is it? Two different times, yeah. Yeah. Why do we use powerful lasers? Yeah, because their ability to make it to the bottom of the water and back. Yes, that's right. Exactly. Essentially, that's what it is. Why is it Why is it so difficult? Everybody's shone a laser before in the air, and you know that they can shine lasers on the moon and have them reflect back off that little mirror that they left behind. It's true. Okay. We can measure the distance of the moon exactly, and we know that it recedes from us. I think it's 10 centimeters a year or something like that. So we know that precisely. Lasers, if you've ever had a laser pointer, a little red laser pointer, they're not very powerful. They probably do damage to your eye if you held it up to your eye for a little while, a few seconds. But they essentially go on forever. You can shine them. You can shine them. Uh, it's probably not a very good idea, and it's highly illegal, and it's why that they've limited the power of lasers in Australia now to, I can't remember what it is, but you used to be able to get 1 watt lasers. 1 watt lasers are extremely powerful, very, very powerful compared to what you get in a laser pointer. Laser pointer might be 5 milliwatts, which is 5 by 10 to the minus 3 watts. So very, very small. But you could certainly shine that on a wall in the distance, and it's going to travel through the air quite well. The green laser is quite a bit more powerful than that, because through the water we can have particles and we can have seaweed, and the ocean floor isn't mirrored. We all know, okay? It's not a perfect mirror to reflect that light back up. So it has to be a very powerful laser. Yes, Larry. Shh, please. Yeah, that's right. So what we tend to find, and this is a close-up view, so Larry's saying that even if we had a nice reflective bottom of a body of water, okay, so this is underwater. I'll draw a fish. Okay, there's a little fish. The infinity fish. He's got a very big fin. This laser has to go down, even if there's nothing in the water. There's no particulate matter. It reaches the bottom of that surface, and if we zoom in to what that surface might theoretically look like, so we take that little area there, and then we zoom in on it, and of course it's sand particles, and it's shaped all sorts of ways like that. And sorry, what this illustrator does is it smooths out my bad lines. But imagine the laser hits this surface here. What it's going to do, because it's only a very fine beam, it's very, very narrow. What it's going to tend to do is reflect there, okay, off in that direction, and it will never reach the plane again. But what's the plane doing? It's not just hovering there, is it, in one spot? It's moving, isn't it? And so that laser, basically, it's just you could imagine it like just lasers constantly as the plane flies over, hitting the surface of the bottom of the lake, constantly, a constant sheet of them. All right? And what will tend to happen is yes, one of the moments that this laser beam hits the floor, yes, is reflected completely away, and the plane never receives that signal back. But the next one, which happens to be in a nice part of is reflected back, and we get the average. We don't get to see that there is the minute bumps in the bottom of the ocean. We just get an average depth of the ocean for an area. Yeah, could. I don't think it would kill it, and it certainly wouldn't. No, it wouldn't slice it in half or anything like that. They're not that powerful. Yeah. You've seen planes before? Yeah. Okay. Oh, actually, I don't want to do that, do I? Just want to copy it. Let me draw you a plane. You guys should draw this. Okay. So why use powerful lasers? Imagine this is. Uh, we're getting to it. That kind of doesn't fit to what we were talking about there before, does it? I'll make this a bit smaller. The plane flies over this body of water, and there's an issue. What about if there's a fisherman? What about if there's a fisherman on his boat? He's just doing a bit of fishing. He's completely innocent, and the plane flies over, and this green laser hits him in the eye. Yes, it could do damage. What did you say, Aaron? The pilot does what? Oh, avoids fishermen. Uh, yes, maybe they do, and maybe they do. Here's a fisherman in his boat. Okay, fisherman in his boat. He's got a rod. Okay, now he's got one of those waterproof hats on. Okay, so yes, and the pilot flies over and shoots him in the eye. Yeah, laser eye surgery. Very, very briefly, obviously, but certainly could do damage to his eye. A laser this powerful that can reach the bottom of the ocean. What they do is they actually put it through a diffraction grating, and we don't get one laser beam. We get a scan of beams. Okay, like this. So it basically takes that laser beam and spreads it out over a much larger area. And so because what happens if you're on a boat fishing and nothing's going on, you're not catching any fish, and a plane flies over, you're out in the middle of nowhere, what do? You look up, don't you? Okay, right? So now you won't, yeah. so so what they do is to safeguard, probably just they it's not going to do too much damage to the person's eye, because it's going to be very quick, and but they also make it so that it's not particularly powerful. It also allows them to scan a larger area, okay, so at the same time, so they're not just scanning one line across the ocean floor. Yes. Yeah. Well, it's it's one laser through a grating that spreads it out. Yeah. Yeah, we'll get to that later. 1 megawatt. Oh, 1 megawatt is a million watts. Sure, it's not a milliwatt. Mega. What? 1 megawatt is 1 million watts, which is very, very powerful. Like, th- thank you, Keem. No. Uh, Keem has actually quoted from our text that it's a 1 megawatt. So is 1 million watts. And to give you an idea about what that could do, I don't know. We'd have to look it up. What is it? I'll just pause the video while we go to another format. We have confirmed that the text says megawatt, and we looked at a YouTube video that says the CNC machine quoted at 4,000 watts. So a megawatt is a lot. Yeah, that's right. And so this yeah, that's right. I'm not sure exactly how many beams, but I know, or the book quotes this distance here as being 10 meters, about 10 meters. So we could potentially, the amount of lasers that could be diffracted from that 1 megawatt laser could be quite a lot. Yes, 10 meters. So what the aircraft is doing is scanning a rectangular grid 10 meters across, 10 meters wide. Meters across. I think it'll be okay. Be effective, yeah, that's right. Good fit. And filleting, yeah. So the water will often have sand particles and other things suspended in it. The laser will scatter. We call it scatter, and scattering is what I was showing before here. Scatter off of off these suspensions. And I've seen it. Is there a question in your homework that asks why use powerful lasers? This was a question somewhere. The water, or any medium, in fact, will tend to absorb the light. You know that light, to pass through any medium, anything other than a vacuum, essentially what it's doing when it passes through a pane of glass is each atom of glass or molecule of glass is taking on that light, doing something, and then spitting it out the other side. That happens, as far as we're concerned, as instantaneously, but some of that energy is always lost. The seabed will absorb the light as well. A light-coloured seabed is best for reflection. And you can imagine if the seabed, of course, it has seaweed on it. If it's rocky and shaped all sorts of shapes, then there's the reflection. Or if it's a dark seabed, it's dark and rocky, which is probably pretty common. The reflection back to the aircraft is not good. That's it for the laser airborne depth sounder. What's that? We have an early minute.